All right, so let's take a look at the last one in the group. We want to find wavelength here. And so wavelength, we can mix together a couple of our formulas. So we had a formula for frequency, and we can use that C over frequency formula and put those together. But overall, we get that lambda is equal to h times c, so that's Planck's constant times the speed of light, divided by the change in energy. Now, conveniently, because of the types of units we have, Planck's constant can come in electron volts, which is good for finding electron volts. And we can go ahead in the speed of light part and actually technically convert that to nanometers, which may seem silly at first glance because it's already like millions of meters or meters per second. But nanometers are nice because that's typically how we look at the wavelength of light. Now, and when we're dealing with X-rays, sometimes we deal with something called angstroms instead, but we don't need that for the scope of this course. And also, it gives us a different constant, but for right now, this will work. The main thing we need to find then is what's the energy released. So, like the last one, technically you could base this off of what you got for E4 minus E1, but then you'd have to remember that was for hydrogen, and then multiply by 69, multiply by 69, and scale it up. Or we can just run it on through similar like we did in question 9. So negative 13.6 electron volts. Z number is not 1, so we definitely need to include it. So we take 69 and square it. Then we've got 1 over 4 squared and 1 over 1 squared. And this time we're not converting to KeV or anything. We just want whatever big answer we get from this. So don't forget to do the 69 twice and to do the fractions, the denominators twice with these exponents. Be very careful when you type this in your calculator and when you work it through. For our energy released, we'll get 60,702.75 apparently. And then now that's perfect. So H times C, again, is already a combined constant, and it's reshifted and scaled for useful units. It's on your formula sheet, and it should be relatively easy to find. But we can use that this is 1,240 electron volts times nanometers, which is actually really great because when we plug in this bottom number, because it's in electron volts, that's going to cancel. So electron volts and electron volts are gone. Nanometers are here, which is what we're looking for. And finally, running that through a calculator to divide these, 0.0204 nanometers. So very, very, very small wavelength because it's very, very, very high energy.